All right, characteristics of stars. Black holes. If you were an astronomer, you might study some of the strangest objects in the universe. For almost 100 years, scientists believed that some stars became black holes when they died. But a black hole is an object with gravity so strong that not even light can escape. So scientists couldn't prove that black holes existed because they couldn't see them. Eventually, astronomers discovered a way to prove black holes exist. They realized that they could detect the matter being pulled into the black hole. That matter reaches such high temperatures that it releases X-rays. In the 1960s, astronomers launched a rocket to record X-rays from outer space. On this first mission, they found evidence for black holes. All right, so answer these questions, 1 and 2. Why was it so hard to prove that black holes exist? And then 2, what subjects other than astronomy would astronomers have to study in order to discover black holes? Might be something that we've talked about before. All right, how are stars classified? All stars are huge spheres of glowing gas. Made up mostly of hydrogen, stars produce energy through the process of nuclear fusion. Astronomers classify stars according to their physical characteristics. Characteristics used to classify stars include color, temperature, size, composition, and brightness. So color and temperature. If you look at the night sky, you can see slight differences in the colors of the stars. Some stars look reddish, others are yellow or blue-white as shown in Figure 1. A star's color reveals its surface temperature. The coolest stars with a surface temperature of about 3,200 degrees Celsius appear red. Our yellow sun has a surface temperature of about 5,500 degrees Celsius. The hottest stars with the surface temperatures of over 20,000 degrees Celsius appear bluish. Size. When you look at stars in the sky, they all appear to be points of light of the same size. Many stars are actually about the size of the sun, which is a medium-sized star. However, some stars are much larger than the sun. Very large stars are called giant stars or supergiant stars. Most stars are smaller than the sun. White dwarf stars are about the size of Earth. Neutron stars are even smaller, about 20 kilometers in diameter. All right, so 2 things you're going to answer here. First, write a sentence that says what the color of a star indicates. And then here, which star shown has the highest temperature and why? Which star is the sun's size? So you've got these 4 to look at to answer those questions. All right, chemical composition. Stars vary in their chemical composition. The chemical composition of most stars is about 73% hydrogen, 25% helium, and 2% other elements by mass. This is close to the composition of the sun. Astronomers use spectrographs to determine the elements found in stars. A spectrograph is a device that breaks light into colors and produces an image of the resulting spectrum. Today, most large telescopes have spectrographs to analyze light. The gases in a star's atmosphere absorb some wavelengths of light produced within the star. When the star's light is seen through a spectrograph, each absorbed wavelength is shown as a dark line on a spectrum. Each chemical element absorbs light at particular wavelengths. Just as each person has a unique set of fingerprints, each element has a unique set of spectral lines for a given temperature. All right, so you're going to apply that. The lines on the spectrum below are from 4 different elements. By comparing a star spectrum with the spectrums of known elements, astronomers can infer each element found in the star. Each star spectrum is an overlap of the spectrums from the individual elements. So identify the elements with the strongest lines in stars A, B, and C. All right, brightness of stars. Stars also differ in brightness, the amount of light that they give off. The brightness of a star depends upon both its size and temperature. A larger star tends to be brighter than a smaller star. A hotter star tends to be brighter than a cooler star. How bright a star appears depends on both its distance from Earth and how bright the star truly is. Because of these 2 factors, the brightness of a star is described in 2 ways: apparent brightness and absolute brightness. Apparent brightness. A star's apparent brightness is its brightness as seen from Earth. Astronomers can measure apparent brightness fairly easily using electronic devices. However, astronomers can't tell how much light a star gives off just from the star's apparent brightness. Just as a flashlight looks brighter the closer it is to you, a star looks brighter the closer it is to Earth. For example, the sun looks very bright. This does not mean that the sun gives off more light than all the other stars. The sun looks so bright simply because it is so close. All right, absolute brightness. A star's absolute brightness is the brightness the star would have if it were at a standard distance from Earth. Finding absolute brightness is more complex than finding its apparent brightness. An astronomer must first find out both the star's apparent brightness and its distance from Earth. The astronomer can then calculate the star's absolute brightness. Astronomers have found that the absolute brightness of a star can vary tremendously. The brightest stars are more than 1 billion times brighter than the dimmest stars. All right. What is the HR diagram and how do astronomers use it? About 100 years ago, two scientists working independently made the same discovery. Both Ejnar, we're going to say just Ejnar, in Denmark, and Henry Norris Russell in the United States made graphs to find out if the temperature and the absolute brightness of stars are related. They plotted the surface temperatures of the stars on the x-axis and their absolute brightness on the y-axis. The points formed a pattern. Astronomers today still use the graph they made as a model. It is called the Hertzsprung-Russell diagram, or HR diagram. All right, the HR diagram shows the relationship between surface temperature and absolute brightness of stars. Place the stars listed in the table on the diagram and note on the table the classification of each star. So, right there. All right, astronomers use HR diagrams to classify stars and to understand how stars change over time. As shown in Figure 3, most of the stars in the HR diagram form a diagonal area called the main sequence. More than 90% of all stars, including the Sun, are main sequence stars. Within the main sequence, the surface temperature increases as absolute brightness increases. Thus, hot bluish stars are located at the left of an HR diagram, and the cooler reddish stars are located at the right of the diagram. The brightest stars are located near the top of an HR diagram, while the dimmest stars are located at the bottom. Giant and supergiant stars are very bright. They can be found near the top center and the right of the diagram. White dwarf stars are hot but not very bright, so they appear at either the bottom left or bottom center of the diagram. All right, assess your understanding. What two characteristics of stars are shown in the HR diagram? What is the relationship between brightness and temperature shown within the main sequence? The star Procyon b has a surface temperature of 7,500 degrees Celsius and a low absolute brightness. Use the HR diagram to classify it.